If there were no gravity, the Earth would not be moving in a circle around the Sun. It would simply travel in a straight line. Scientists back in the 1600s and 1700s knew this, and they were perplexed. What force is causing the Earth to turn? What force is pushing the Earth perpendicularly to its velocity? This was a puzzle, and it's one that Newton solved with his law of universal gravitation. Here's the proportionality form, here's the equation form. And we can write this as a picture showing two masses, and they feel equal gravitational forces. That force depends on the inverse square of the distance between them. R is the distance between them. We measure it in meters. So this law solved a big problem that Newton faced. The law of universal gravitation explains where that turning force comes from for objects that are in orbit. Okay, so my question next is, does this mean the Earth is falling? Let's remember what it means to be in free fall. Free fall, that's where, you're standing on a surface, you throw a ball, and it falls to the ground. It's a projectile, and everywhere on its path, the ball feels only one force, the force of gravity. That's free fall, right? Let's turn back to orbital motion. Imagine we have the tallest mountain in the world here on the North Pole, and you climb up and you throw this ball as hard as you can. And what happens? It hits the ground below. And then you try throwing a little harder, and you make it into the ocean. And you throw a little harder, and it lands in Europe. Then you go down, you get a personal trainer, you start working out, and you get so strong that when you climb back up, you can throw this thing right to here. And then you try a little harder, and you throw it to here. Then you realize, well, wait a second. Maybe there's a sweet spot where I can throw this ball, and it keeps falling. It just never lands. That is what's happening when objects are in orbit. They are falling, but they never land. At every moment, the only force pulling on them is the force of gravity. Right here. They are falling toward the Earth. They're being pulled down. Nothing else is acting. At every single moment, they are in free fall. That's kind of a wild idea. That orbit is the exact same principle or behavior as an apple falling from a tree, or a projectile, a ball being thrown into the air. They are the same. They are both falling. Let's write that down in our notes. Objects in orbit are in free fall. That's where they only feel the force of gravity. And here's a picture summarizing that as well. So the final thing will be to do some practice. We can work through this one together, and then you all can try some on your own. The moon has this mass, and here is its orbital radius. That's from the center of the Earth to the center of the moon. Okay, find the gravitational force. You can use this equation. Plug in those values. We know all of the values. the mass of the Earth is right there. I'd like you to write out the step where you show plugging in the values. Show that step where you plug in the values. But if you do this on your calculator, I encourage you to use the second EE button. I'll show you that when I divide by the radius squared. And also, I want you to do it in all one step. I think that can actually help avoid mistakes. Okay, so next I have to divide by r squared. And check this out, I don't even need parentheses when I'm using this second comma, second EE. When I do second EE, it's like saying times 10 caret, or times 10 to the, and so, okay, well, what is it? It's times 10 to the 8. And if you square this, it will only square, it will square the 3.85 E8. If I hit enter, there's my answer. And that is the exact same as if I had put parentheses. So the second EE button is really, really good because it avoids the need for parentheses like we would normally expect on the calculator. Watch, if I do this, I get the exact same answer. So my answer is 1.97, but don't forget the exponent. You've got to check for the exponent at the end. So the answer, after you plug in the values, 4.97, oops. Times 10 to the 20. And the force unit is newtons. 1.97. How hard is the Earth pulled by the moon? That's a trick question. They feel the same force according to Newton's third law. To find the acceleration of the moon, well, we know the net force is equal to the force of gravity. But we also know net force equals mass times acceleration. So plug in the net force on the moon, plug in the mass of the moon, not the Earth, the moon's mass, the smaller value, and that's going to be the 7.35 times 10 to the 22. This is 10 to the 24. This is bigger. And when you calculate this, you'll get 0.00268. Let's see. 2686. And if you want to round that for sig figs, what is it, 3 sig figs? I hope so. Meters per second squared. Next, we calculate the speed. Well, we know the acceleration, we know the radius. There's an equation that says in circular motion, here is your speed. So we can plug in the value here, we can plug in the radius. You'll cross multiply to get v squared alone, and then you'll have to square root both sides. And your final answer, let's see. So I multiply that acceleration by the radius. I square root both sides. I square root both sides. And I get 1016.997. After you show the other work. And we could round that to 1020 if you want sig figs, or just 1017. Next, we have to find the orbital period. That's capital T. If we know the speed and we know the radius, there's an equation that relates the two. Plug in the speed, plug in the radius. Remember, you have to get t out of the denominator first before you go solving. So multiply both sides by t and then divide both sides by speed. And when you do that work, when you show it, the final answer should come to, let's see, so I've got 2 pi r, and r is 3.85 second EE 8. Then I have to divide by the answer there, and wow, 237, let's call it 2.37 times 10 to the 1, 2, 3, 4, 5, 6. And we want to convert that value out of seconds. So let me divide by seconds so they cancel. And into days. Well, let me first change it into minutes. I know there are 60 seconds equaling 1 minute. So this fraction is simply the same as multiplying by 1. I'm not changing the value when I multiply here. I'm only changing the unit. Okay, now let's cancel out. Seconds have gone away. Let's cancel out the minutes. And what could I convert that to? Well, I know the equivalent amount of hours. 1 hour is 60 minutes. And minutes are canceled. Finally, we have to get rid of the hours, and I know the equivalent number of days, amount of days. Specifically, 1 day is 24 hours. And this multiplication here will cancel out the hours. Now I just multiply across everything in the numerator. I divide by everything in the denominator. And what do we get? Over 60. Divide the answer by 60. And I also have to divide the answer by 24. 27.5 days. That's an interesting value. It's about a month. What are we talking about? Oh yeah, the time it takes the moon to move around the Earth. But this is exactly the time it takes for all of the cycles of the moon to occur. This is the value you learn in like grade school, where you learn about, the crescent moon and the full moon, and it all starts over after about 27.5 days. That's pretty cool. Nice work. Thanks for watching.